In this problem, we're going to take a look at the pressure on a diver under the sea. So we've got a scuba diver here. He's only down around 30 meters. In fact, he's precisely at 30 meters. Well, here we give you the density of seawater. It's 1.31 grams per cubic centimeter. We tell you the gas pressure. You're at sea level, no, above you at sea level. It's 1.0 atmosphere today. What I want to know is find the total pressure. So the pressure total on diver. To start with, don't try to solve this. Instead, what are all the parts that you would need to know? So the first bit, pause, try to solve what are all the factors that are going on. Then come back, we'll discuss them, and then we'll give you a try at solving the value. All right, if you're back and we're thinking about it, what's going on with this diver? Well, for all intents and purposes, the gas is pressing down. Well, it doesn't matter that it hits the water. I mean, it's pressing down on that, and that's pressing down on you. You know, just because you hold something over you, if somebody steps on the thing you're holding, you feel their weight. The fact that there's interrupting matter just means that they're standing on it. It's still pushing down into you. So all that gas is pressing down. And then there's also the water. The water is pressing down as well. So our pressure total is really going to equal the pressure of the atmosphere plus the pressure of the seawater. Well, we know the pressure of the atmosphere, so that's not too hard. What about the pressure of the seawater? Think about where the pressure of the atmosphere comes from, right? If we have a column of material, and there's gas inside it, generally we tend to do things like 1 inch by 1 inch by to space. We find the weight of all of the gas in that column because all of that gas is pressing down. And so on that square inch base, there's 14.7 pounds of gas pressing down on that 1 inch squared. That's where we get the PSI, 14.7 pounds per square inch for the standard atmosphere. Well, that's not any different for the water. There's stuff. We just have a different column. Over here, I have a column of water. I can build whatever column I want. There's going to be a weight of that water. That weight is pressing down on the base of that column. So I can actually find the pressure of the water in the same way I found the pressure of the gas in PSI. It's just the weight of that water in that column pressing on its base. So to find our total pressure, can you find these two components? Go ahead and pause. See what you can do to find the pressure of the water in order to find that total pressure. All right, if you're back, well, let's think about what units do we want to be in. Like there's a lot of pressure units. I've got pounds per square inch over here. I've got atmospheres over here. I'm trying to find the weight of water in that column. How much water is in here? Well, it's not pure water. We were given a density. It's seawater. There's ions of chloride and sodium and all sorts of stuff. As a result, it weighs more than pure water would. Well, it comes in grams and centimeters cubed. It's kind of easy to do calculations in metric, so let's just do this all in metric. I know I'm 30 meters deep. I know the density in metric. What if I convert my pressures all to be metric? Well, 1 atmosphere, remember, is equal to 1.035 kilograms per centimeter squared, which is also, times 1,000, 1,035 grams per centimeter squared. Why do we want that? Well, a column. If I'm going to make a column, how easy would it be to have a column whose base is 1 centimeter by 1 centimeter. Instead of doing the inch column, let's just do a metric centimeter column. To enhance the view of this a little bit, I have a column going all the way up to the surface. It's 1 centimeter by 1 centimeter by, well, we know it's 30 meters deep. 30 meters is going to be 3,000 centimeters. So remember, 30.0 meters, every 1 meter has 100 centimeters for 3,000 centimeters. Well, that means every 1 centimeter we go up, if we kind of draw across, so 1 centimeter tall, I could just cut this column into a bunch of 1 centimeter tall cubes. Each of those cubes ends up being, forgive my art skills, 1 centimeter by 1 centimeter by 1 centimeter. Ends up being 1 centimeter cubed. If I can figure out how many centimeters cubed I have, which will be 1 times 1 times 3,000, so we have 3,000 centimeters cubed in the column, well, I know how much that's going to weigh. That column is filled with seawater. Each one of these little centimeters cubed is going to be 1.31 grams. So here's 1.31, here's another 1.31, here's another 1.31, and so on and so on and so on, all the way to the top. All 3,000 of them. Well, every 1 centimeter cubed is 1.31 grams. So this is going to be 3,930 grams. I can actually find the weight of water in that column. The total of all of that is going to be 3,930 grams of seawater. That is the weight of water pressing down on the base. Just like the total weight of all the gas in the column to space was 14.7 pounds, all pressing straight down on its 1 inch by 1 inch. This is the weight of the water pressing straight down on our centimeter by centimeter base. This means I know my water pressure. What is my water pressure? It's the weight over the area. It is the 3,930 grams over the centimeter squared base. So what is my pressure total? What's going to equal the original pressure from the atmosphere, which was 1,035 grams per centimeter squared, plus the pressure that we determined from the weight of the water, which was 3,930 grams per centimeter squared, for a total pressure of 4,965 grams per centimeter squared. Well, that is several times. It's almost 5 times the atmosphere itself. It took the entire atmosphere from space to the surface of the ocean to give you 1,035 grams, but it took only 30 meters to give you almost 4 times that. There's a lot more mass of water. Air is thin and spread out. There's not a lot of it for the same volume, so you need a much bigger volume to have a reasonable weight. Water is very dense. If you ever dive in a pool, you feel that pressure very quickly. You have to go up thousands of feet in an airplane before your ears kind of pop, but you only have to dive 10 feet underwater before your ears start feeling like they want to pop. The pressure change is similar. 10 feet underwater is about the same as 8,000 feet going up in an airplane, because the material that you are referencing is so very different. But to find our pressure total, we just had to look at the weight of everything above. It was both the gas and the water combining together, all pressing down on our diver.